Algebra 2, Chapter 13.3, Exponential Decay Functions. Here we have an essential question. How is the graph of g of x equals a times b to the power of x minus h plus k, where b is between 0 and 1? And that's your distinction, exponential decay function. In an exponential growth function, you had b, your base, greater than 1. Here, you're looking at a base less than 1 for decay. And we're looking at this function here, f of x equals b to the x, and you're going to have a transformation used based on what a is, what h is, what k is. And we're going to examine that in this lesson. Okay, uses of exponential decay. There are many real-world uses of exponential decay, and here are 4 of maybe the most notable. You have population decline, depreciation. If you're going to buy a car, well, you're going to be interested in its depreciation to get that car fairly priced. Radioactive decay involving half-life, oil and gas production decline. Very important in our lives today. Explore 1, graphing and analyzing f of x equals 1/2 to the power of x. And so we're going to examine f of x equals 1/2 to the power of x first. And what we have, if we plug in -3 to this function, we have 1/2, which is 0.5, times to the power of -3. Okay, what is that going to be? Well, it's going to be 1/2 times 2 to the -3rd power. Well, that's going to be equal to 1 times 2 to the 3rd power, which is going to be equal to 8. So that's how we come up with this number already. And then when you do the same thing for -2, so we have 0.5 to the power of -2, that's going to be 1 over 2 to the -2, which is going to be equal to 2 squared, which is 4. So 4, if we plug in -1, we get 2. If we plug in 0, we get 1. If we plug in 1, we get 1. We get 1/2 to the 1st power is going to be 1/2. If we plug in 2, we get 1/4. If we plug in 3, we get 1/8, and so on. And now it says B, what is the end behavior of this function? Does the end behavior of this function appear to be as x increases? What are we going toward in output? Well, as x approaches infinity, f of x approaches what? 0. So that would be our end behavior as we go to the right. Now plot the points on the graph and draw a smooth curve through the points. We plug in -3, we get 8. We plug in -2, we get 4. We plug in -1, we get 2. We plug in 0, we get 1. We plug in 1, we get 1/2. We plug in 2, we get 1/4. We plug in 4, we get 1/8. And so it says draw a smooth curve. I don't know how, this pen is kind of glitchy sometimes. I'll do the best I can. That's about as good as can possibly be done. Okay. And then same principle, but for 1/10 to the power of x. Well, if we take we already have for -3, we get 1,000. Well, if we have 1/10 to the power of negative 2, we get 1 over 10 to the negative 2, which is the same as 10 squared, which equals 100. So 100 here. If we plug in negative 1, we get 10. If we plug in 0, we get 1. If we plug in 1, we get 1/10. If we plug in 2, we get 1/100th. If we plug in 3, we get 1/1000th. And as far as what to draw this in, if we put in negative 1, we get 10. You can see negative 2 and negative 3 are totally off the chart. If we plug in 0, we get 1. If we plug in 1, we get 1/10. If we plug in 2, we get 1/100th. So we get something that's going to be even harder to draw than the other one. Oh, that looks terrible. Freehand drawing is challenging enough without a glitchy pen. Okay, this is about it's going to have to work here. You can see how really the graph flattens out very quickly to the x-axis going forward. Okay. Now the domain, here we have our domain in set notation, and we'll just fill in the chart. We have on the left the 1/2 to the power of x, to the right we have 1/10 to the power of x. Well, the domain for both of these is exactly the same. Okay. So in the range, we have y such that y is greater than 0. And the same for this other one, y such that y is greater than 0. And behavior as x approaches infinity, as x approaches infinity, f of x approaches 0. As f of x approaches infinity, f of x approaches 0 in each instance. And behavior as x goes to negative infinity, when we have negative infinity for both. Now notice that the basic characteristics up to this point are exactly the same for each. And the y-intercept in each instance is going to be the point 0, 1. So the key features for M behavior, domain and range, etc., for both of these functions is exactly the same. Boundedness also, bounded below. Okay, of the two functions, f of x equals 1/10 to the power of x decreases faster. And that's because the depreciation rate, the greater depreciation. Okay, make a conjecture, we'll skip that. Predicting transformations. Okay, we have this thing right here, which is what we call in the language of transformation, we call that the value of A, which impacts vertical stretch or vertical compression. So 3 times 1/2 to the power of x will vertically stretch by a factor of 3. The graph of g of x, g2 of x equals 1/4 times 1/2 the power of x, with the graph of 1/2 the power of x vertically compressed. By a factor of 1/4. Okay, now we have this b, we have this graph, we have negative 3/4 times 1/2 the power of x. What does this negative sign do? It reflects across the x-axis. And vertically, what is this 3/4 going to do? Is that 3/4 less than 1 or greater than 1? Less than 1. So we're vertically compressing by a factor of 3/4. Okay, and then the next one, g2 of x equals negative 1/5 times 1/2 power of x. We are reflected across the x-axis because of the negative sign by a factor of, wait, I want to put this x-axis up here, and vertically stretched by a factor of 5. Okay, and then we have these other below, they're similar. Now we have this 1/2 to the power of x plus 1. Well, it's going to be 1/2 translated is this x plus 1. Remember, we have this a times b, which is the base, to the power of x minus h plus k. So this h and k involve the horizontal and vertical translations respectively. So this x plus 1 is going to be translated 1 unit. This plus 1 is going to do what? Translate 1 unit. X plus moves to the left, x minus right. So 1 unit to the left. That's in the place of h. The graph of g2 of x equals 1/2 to the power of x minus 4 will be graph translated 4 units to the right. To the right, there we go. Then this one below, similar, 2 units to left. This graph here, x minus 3, 3 units to the right. Okay, well, then we have this k position is going to be up and down. 1/2 the power of x plus 3 will be 3 units up. This next one, minus 5/2 will be 5/2 units down. And so in this next one, 5 units up. This last one, 2 units down. But you should be quite familiar as many of these types of functions we've gone over in the year. Okay, next, combined transformations. And essentially, we're going to, what they recommend doing is taking 2 reference points and translating these reference points. And so the first reference point from the original graph, you take an input of, you're looking at the y-intercept, 0, 1. So it's going to be the y-intercept. And the next reference point is going to be, they suggest using negative 1/2. So, or negative 1. So that's going to be your second reference point. And then what we're going to do is translate the reference points to transform the graph of the function, essentially. And here they give an example of what you do. And I graphed an original parent function in the calculator. This is the function 1/2 to the power of x. And then you're going to put this form in here. What is it going to do to these 2 reference points? They put the 2 reference points in the original function here. Well, what is that going to do? Well, the drawing below shows you, and in the graphing calculator, this is what it looks like. Come down and turn on this function here, activate it. And there we see in red, and this original reference point here goes 2 to the right essentially, and the second one over here will go up here. So it's just we're going to be doing exercises in subsequent lessons throughout this section, and that's as far as I want to go for this introduction today. So just stick with it and we'll work out some problems on these. Thanks for viewing.